guys can see the screen okay, I'm guessing.
Mm-hmm.
Okay, so back at Fourier transforms again. And this will line up a little better with lab 2 that you guys will be starting tomorrow, but you'll have everything covered last lecture, this lecture about the Fourier transform. And today we're going to be talking more about, we've talked about Fourier's synthesis, Fourier's hypothesis, Fourier's trick. Today we're going to get much more into like the transforms of trying to go between time and frequency space and what you would expect to see for different signals, which I've shown down here. We'll be going over those in some detail. So we're going to do a quick recap of last lecture, just a quick refresher, get your mind in Fourier transforms and frequency space again. We're going to start off by talking about different ways that you can mathematically represent a Fourier transform. We've been mostly working with sines and cosines in the trig notation, but how else can you write these out? We hinted at that last week when we were talking about Euler's formula. Then we'll get into the difference between working with continuous data, which we've kind of been talking about hypothetically, and you've been seeing with how we've been mathematically writing things in terms of integrals over all space, but in the lab and when you're working with actual data, you never have an infinite data set. You're working with discrete data sets. So what does that mean in discrete versus continuous, and how does that change how your data is represented? And then lastly, we'll be going over useful signals and what their Fourier transform is. And this is really useful. In lab 2, you'll be going over this, but useful just as being a physicist or an engineer. If you have a signal, what would you expect to see? If you see something that's different than that in the frequency domain, trying to understand what the discrepancy is. So we'll be going over that. Just recapping last lecture, I have this written out as text since it's a recap. I'll be getting into writing the notes on the next slide, but recall that why Fourier transforms are important. We discussed in solid state medical physics and the like, and we went over Fourier's hypothesis both conceptually and mathematically. So remembering that any periodic function, or we basically said any function, can be represented as a sum of both sines and cosines. So that was the big takeaway there, that if you use sines and cosines, you can represent any signal that you might have. And we got into a little bit more detail that they're integer multiples of a certain frequency of the original period. So when we wrote this out mathematically, you can see that we have our sines and cosines showing up here, the integer multiple showing up with the n over here, and the amplitude of those components coming out in these constants here. We went and derived that a naught here with the n equals 0, that this equals the time average of your signal. And we showed that using this hypothesis, we could build up a signal using in a technique called Fourier synthesis. Also, these points here are kind of pointing out why we use sines and cosines. That's the basis set. So they're orthogonal functions. They have very different, they have a large difference, just like when we were talking about colors when you're printing or doing displays, that you want your basis set to be quite different from one another, so you can represent many different combinations. We talked about Euler's formula, that we can express these in exponents, and the fact that if you have a sinusoidal signal, if you pass it through an instrument, it'll stay a sinusoidal function, even if there's a variation. So these are why Fourier's hypothesis, why Fourier transforms are built from sines and cosines. So that's a recap from last week. Any questions from that, since you've had a little bit of time to digest that since last week? Okay, so we'll move on to the new stuff today. First, getting back into some of the math, we're going to talk about different ways that you can represent Fourier transforms. So I'm going to divide this into some quadrants. We're going to show 4 different representations, where the first one is what we were mostly working in last week and on this previous slide, using this type of notation with the sines and cosines. So the trig notation here, where we can represent this as A, some constant times a cosine with a frequency times time, some B sine omega t. And I'm leaving out those integer multiples just to keep this as the most general formula as we can write here. And like I said, this is what we've been using so far. So it really shows the representation of Fourier's hypothesis in a mathematical form, the verbal way that we've been explaining it. But it has drawbacks. It's the least convenient notation, I would say. I'm missing, can't spell, and you'll see that's a theme throughout this semester. Least convenient way of notating this because it's lacking phase information. That instead of using that the phase is coded in the cosines and the sines and the combinations of those. So if you have your signal, if your signal changes phase, I'm going to write that as a delta phi there. Your A and B components would change. So any phase shift, you would have to recalculate this expression every time. Which is not very easy to do. There's no clear trend in how A and B change for a given phase shift there. So that's the drawback of this notation, which leads us to the second notation that I'm going to talk about, which includes phase instead. And we're just going to write this as capital A, our amplitude times some integer, the frequency, plus a phase component. So we're increasing, or we're including a phase component here with this phi. And I wrote this with cosine, but you could use sine. It's an arbitrary choice. And here for each integer, n, there's going to be an amplitude, our capital N, A sub n, and there's going to be an angle, a phase shift, a phase associated with each integer. So by some n there. So if we
equation, should there be a time at all?
Yes. Good grab. And that's missing in the notes I've uploaded as well. Thanks, Jack. So for each integer, we have that. And if we want to go, I'm going to circle this guy. If we want to go from our first notation here to our second notation, we're going to use some trig concepts and a trig identity to switch between those two. So we're going to use a trig identity that cosine of alpha plus beta is equivalent to cosine alpha times cosine beta minus sine alpha times sine beta. So if we take our expression up here, that means that capital A times cosine times, I'm just going to write this simply with omega t plus phi is going to be the amplitude. We can pull that out. The amplitude times cosine omega t times cosine phi minus the amplitude times sine omega t times sine of phi. I'm trying to write that better. There we go. And if we compare this notation, this expression here, after we apply the trig identity, if we compare this to our expression with the first notation over here, we can clearly see that lowercase a in the first notation is equivalent to capital A times cosine of phi. And lowercase b is equivalent to negative a times sine of cosine, or sine of phi. So then we can rearrange this and we can find that capital A, our amplitude in this second notation, would be equivalent to lowercase a squared plus lowercase b squared, the square root of that. And that our angle phi here would be the arctangent of negative b over a. So if we want to go from this first notation to the second notation, this is how we would convert between those. And looking at these expressions, it may look familiar to when you're thinking about triangles, of course, trig and stuff like that, that we can also visualize these constants and the representation on a complex plane. And this is going to become important in some of the fourth notation that we're talking about as well. So it's written kind of small, but this is the imaginary axis on the y. And then we have a real axis here. And we're going to represent this as a phasor. A phasor is a vector that's pinned at the origin here. So if we draw this out, we can represent this as a phasor where the magnitude is capital A and our angle here, phi, is the angle between those, which then if we think about this relationship, we can then say the projection on the real axis over here is going to be lowercase a, and the projection on the y-axis, the imaginary axis is lowercase b. So this is another way to visualize the relationship between lowercase a, lowercase b, capital A, and our angle here. So that's the second notation. The third notation is applying Euler's formula, where instead of representing this as sines and cosines, we can instead represent this in terms of exponents. So we can say a times the exponent of I, which is the imaginary number, times omega t plus our angle phi here. So this is our third notation. Where the important thing to note here is capital A is a real number. And this is the application of, like I said, Euler's formula. I'm just going to write 2 to represent this up here. So this is very useful because where A is the real number, what that means is that that's the physical wave. That's the real part. And since we're working in lab, that means that we're working with real data. We're not working with imaginary data. So this expression is very useful. So we can also write this out as the real portion of A times E I omega t plus phi is equivalent to A times cosine omega t plus phi. So that's how this is very useful for working with real waves. And again, for each integer n, there's going to be an amplitude and an angle or a phase shift there. So this is the same notation as part 2 here. So the A that's capital A here is equivalent to the capital A in the third notation. The phi is the same in part 3. So they're equivalent. But the benefit, like we discussed in last lecture with using Euler's, is that exponents can be easier to handle. mathematically. So that's why you may prefer to use this type of notation over the second notation we mentioned. And then finally, the fourth notation is when you're dealing, when not everything has real amplitudes, that you may have imaginary components as well, where it's going to look very similar to the third notation, but we're using C here times EI omega T, where C is a complex number and the complex meaning that you have its complex conjugate, where it's going to have an imaginary component, where this is complex and its conjugate, indicated by the asterisk here, would be changing that imaginary number to a negative, where then C times its complex conjugate would be equal to x squared plus y squared here. And we can then say the magnitude of C would be the square root of C times its complex conjugate, which would be the square root of x squared plus y squared. There's no F. So here the C can account for the phase information within that constant. So simplifying this even more. So there's going to be a value of Cn for each integer frequency value, omega n. So the benefit here is that you can account amplitude and phase in the same constant. So it's just a simplified version of that. So we can write Fourier's hypothesis in a very simplified way using this equation compared to what we showed last time. Let's see. So we can write for a signal in the time domain, it can be represented as a sum over all space from negative infinity to infinity of just Cn EI n omega t. So that's much more condensed than what we had written last week here, just showing the simplicity of that. So this is Fourier's hypothesis in this notation. So then relating this fourth notation to some of the other notations, some of the relationships would be your constant at a value of n equals 0. So C naught would be the equivalent to A naught. For higher values of Cn, it would be An minus I Bn divided by 2. And then for any negative values, An plus I Bn divided by 2. So this divided by 2 comes from the complex conjugate aspect, that Cn, or C of negative n, sorry, C of negative n would be equivalent to the complex conjugate. So you only have to calculate the positive n terms. So that's from going from notation 1 to notation 4 here. If you want to convert between the lowercase constants out front to the uppercase ones. You can also convert between the second and third notation to the fourth notation, thinking about, I'm going to star this plot here. The spot here is a nice way to think about going in between those constants as well. That if you have a phase change, we'll talk about this in a later slide, if you have a phase change, how this shifts. I'd say keep this figure in mind for all of these notations. And I'll show in a later slide how this accounts for how A, B, uppercase A, phi will change based on how your signal is changing. So any questions right now with any of these notations? Check the chat. Okay. So we can move on. And I wanted to introduce those notations so we can write and represent Fourier transforms in a nice condensed way, and inverse Fourier transforms. So we've been talking in the past lecture, on the past slide, we talked about Fourier's hypothesis that you can build up signals using combinations of sines and cosines. We talked about Fourier's trick last lecture, where you can use the properties of having the integer multiples of sines and cosines to either equal a constant or have them all cancel out to be 0 when you integrate over them. And we talked about Fourier synthesis, so building up a whole signal from sines and cosines. But the most common thing that's used in relation to Fourier is the Fourier transform. So that's the most common terminology that you'll use, where we're going to define a Fourier transform as for a given signal in time, where time is the key here, what are the frequency components that contribute? That's what a Fourier transform is trying to answer. So to find the frequency components, we're going to represent that with capital F omega. That's the function that we're trying to find that represents the frequency components that are there. And we're going to represent this mathematically as 1 over the square root of 2 pi over the integral from -infinity to infinity. Our function, our signal in time is lowercase f of t times the exponent e I omega t dt, where it's important to note that this is positive here. So this is how you perform a Fourier transform, going from time to frequency, answering what frequency components contribute. So an inverse Fourier transform, I'm going to say this is ft. I'll say this is ift. So an inverse Fourier transform is the opposite of that. So for a given signal in frequency, what are the time components that contribute? So we'll represent this with lowercase f of t, and it looks very similar with one difference. 1 over the square root of 2 pi. Again, integrating from -infinity to infinity, capital F omega times e negative I omega t, or omega t d omega. So please note that the differences with that positive or negative I in the exponent, or the positive or negative, that's an important thing to do. So these equations and this definition of Fourier transforms and inverse Fourier transforms, these equations are the mathematical description of how to go between conjugate variables. And last week we discussed some other cases of conjugate variables, and you can do Fourier transforms where instead of time and frequency, you would then plug in your other, your Cartesian coordinates, k-space, and the Fourier transform is the way to go between those conjugate variables. But for this class, everything is in time and frequency there. So one thing to note in these equations here is the limits on the integrals. That you'll note that they go from negative infinity to infinity. So when you guys are working in the lab or your lab partner is working in the lab, are you guys, is this representative of the data we have at all? If we just look at these equations. Are you guys measuring forever? Are you measuring since the beginning of time to the end of time? No. So this differs from what the actual real data is that you're dealing with in the lab. So that would be defined on this previous slide, negative infinity to infinity. That'd be continuous data, but you guys have discrete data. One, it's discrete in that you are collecting it for a certain amount of time. It's also discrete in that in the frequency that how often you're collecting your data as well, that you don't have infinite time resolution and length, but also the space between data points as well. So in reality, we never have continuous data. So how do we take these mathematical concepts of continuous data and then handle it in the lab? And that's where the concept of the fast Fourier transform comes from. So you'll see this abbreviated FFT, where the fast is just speeding up the computation. And we don't have time to go into all the details. Like I noted that there's entire classes devoted to Fourier transforms, but you should be aware that the fast Fourier transform is a way to reduce the complexity of the calculations. And discrete data, you also hear this represented as like sparse data, sparse matrices. And a lot of the mathematical tricks, the techniques that were developed with the fast Fourier transform were developed in the 1970s. And if you're interested in that, I encourage you to look at some of the history and that there's different methods to the fast Fourier transform. There's different selections you can make. So if you are getting into some data analysis that's working with Fourier transforms, it's worth trying to understand which algorithm is behind the computational language that you're using. If you're using MATLAB, what's behind the FFT function that's built in, or in Python, in the package you download, what's the math that's behind there? Because there are different methods to the fast Fourier transform. But for those of you that might be interested in how this speeds up the computation, this goes from an n squared type problem to it goes to a problem where it's n times the log of n. So this is a fast Fourier transform scale. So let's say you have a data vector that has 1 million data points, 10 to the 6 million data points. If you just try to handle a Fourier transform with what you could do, that would take scales n squared, so 10 to the second, but the fast Fourier transform methods scale to 4.2 times 10 to the 7th if you do that calculation. So you're getting basically a factor of 5 improvement in the speed, hence the term fast. So that's just a bit of a side, but realize when you guys are working in lab, when you're working with MATLAB, when you're working in Origin, that you're using fast Fourier transform algorithms to do the Fourier transform, to do an approximation to speed it up and get a pretty good result there. And some of the aspects of working with discrete data. I'll write this. We're going to keep talking about discrete data, but also thinking in terms of frequency, which is going to be the goal of Lab 2 and what you're going to be working with, is that how your data is represented because it's discrete will have some differences. So this will change the amplitude that you see. So point of this slide, what I'm trying to emphasize is thinking in frequency and time versus frequency. You're going to start with signals in time. You're going to convert them to frequency using the Fourier transform. How does the amplitude of your signal in time relate to the amplitude of your signal in frequency? So you'll be going through this with simulations, with actual data collected on the instruments. But if your signal, let's say your signal doubles in amplitude, your Fourier transform amplitude should also double. So that's, I'm giving you what you should expect to see tomorrow. But if you see something different, you should work through that. And talking about the amplitude is also related to the discrete aspect of your data. That note that the y-axis, so if you're saying this will be time, this would be your amplitude here, the magnitude of your signal, or if you're working in frequency, you would also have amplitude here. So if you start with some signal and you double that, you should expect to see the sky double over here. But the y-axis that you see in the frequency domain, realize that unlike in the time domain where that might be voltage, you're not going to have voltage on your y-axis here in the frequency domain. The y-axis has to do with the components or the magnitude of the contribution at a given frequency here. So if we're talking about sines and cosines, the different notations there, it would be that lowercase a, that lowercase b, or the capital A that we were talking about there, capital C, depending on your notation there. So your y-axis, the scale will depend on the length of your signal. When you're dealing with discrete data. So because of that, I want to note that you can either notate your y-axis scale in terms of arbitrary units, or you can normalize your data. So the magnitude is 1, or the area under the entire curve, it sums to 1. So that's how you should represent your y-axis there. And I'm notating this because in Lab 2, in past years, people turn it in and they'll put voltage on the y-axis scale. That's not what is actually the label that should be there. So thinking about the units that would be in the y-axis when you're in the frequency space. And I'm saying that it's okay for you guys to use arbitrary units or normalize because we're more concerned about the shape and the size. Let's say size is like the relative magnitudes there. So I just want to point that out, that the scale will depend on the length of the signal. If you're dealing with a short chunk of a sine wave versus a long one, that will change the magnitude of the amplitude there. So just a little comment on the amplitude there. Thinking about time versus frequency here, that we're going to be going over some examples with some different functions, but realize that there's an inverse relationship in terms of the period or the length of your signal in time and frequency. So if you have, the longer it is in time, the shorter it is in terms of frequency. So we'll be showing that, and you'll be doing this in lab, that let's say if you have a pulse in time, that means it's going to be narrower, your frequency domain. And likewise, if it's shorter, then this is going to broaden out. And we'll be going over these shapes in the next slides. And then in terms of phase, remember the equation that we wrote a couple slides ago, that the relationship has to do with this, the sine and cosine components here, the magnitudes, that there's a role in the complex notation of the real and imaginary. So I wanted to just, this is why I wanted to expand upon that with those different notations, that the y-axis is our imaginary axis, the x-axis is our real axis. And let's say we're representing something that has a phase difference of, let's say, pi over 4 or 45 degrees here. So we can say with those notations that the magnitude of this phasor is capital A, or we can say that the magnitude in the imaginary axis is lowercase b, and the magnitude in the real axis is lowercase a. That if you had a phase shift, let's say you want to shift, you shift your signal by 180 degrees. What that would mean, or how you could represent this on this axis, is this would rotate 180 degrees. So then, based on our real and imaginary axes here, capital A would stay the same. So I'm going to say A initial equals A final. But our lowercase a final would be equivalent to negative A of our initial, and B final would be negative B of our initial. That you can see it's going to be negative B here, negative A. So this representation on these axes can represent the phase shifts. It can represent the changes in the sign, or even the magnitude of, just the sign of your sine and cosine components. So this is a nice way to visualize the phase shifts. And then finally, the waveforms, when you're thinking in frequency. So if you have a sine wave, if you have a top hat, we'll be going over those, but also realize that the difference in what you would see in frequency if you have a periodic versus non-periodic signal as well. So in the first lecture, we talked about a sine wave for a sound wave for a certain note. And we showed that, or I just sketched out that you could represent that as a single peak in the frequency domain. So that's an example of a periodic signal. And they will have discrete frequency components. But when you're actually collecting data, and I mean, in the lab, you're going to be very nicely showing sine waves or square pulses that are periodic. But when you're actually doing experiments, you might not have very clearly periodic signals. We can call those general signals. That are, we can say, non-periodic. And those are going to have complex continuous distributions of frequencies in the frequency domain. So that's giving you guys a little bit of an idea of things to consider in time versus frequency. The presentation on this slide might be getting a little ahead of myself and your understanding, because you'll be going through this in the lab, and we'll show this in the next slides where we'll talk about specific waveforms. But At this point, I want to stop if there's any questions about Fourier transform, fast Fourier transform, some of these concepts about how to be thinking about in the frequency versus the time domain. Any questions? Okay. So for the last chunk of the lab, or chunk of the lecture, we're going to be talking about Fourier transforms of useful functions. And it's beneficial to want to know certain signals, what their Fourier transform is, so you can deal with these basically for memory. You can check and make sure that what you're getting out from your equipment and your instruments or your code is actually like working like you expect it to be. And it's also a way that you can decide what non-periodic functions or periodic functions you'd like to use when you're designing an experiment. I'd like to point that everything that I'm talking about in lecture today will be also explained in detail at the end of that chapter 1 of A Student's Guide to Fourier Transform. So you could also look at the derivations there for a different source. But I'm going to walk through, I'm going to try to number these guys out of different signals that we're going to go to in detail, with the first one being a top hat function. And that's going to be a single pulse, single square wave pulse. And we're going to represent it very creatively with a capital pi symbol, just because it looks like the signal that you would have with a top hat. It looks similar to the shape there. And we're going to say for a given top hat function, we're going to represent this with a certain width of lowercase a that I'm going to notate here, given in time. It has these following properties. It's going to equal 0 from -infinity to half the pulse width divided by 2, negative. It's going to have an amplitude of capital A from negative lowercase a over 2 to positive a over 2. That's a less than signal. And then it's going to be equal to 0. That value is greater than that all the way to infinity. So we can sketch this out. We're going to say it's centered around a time of 0. This is our x-axis is in time. And we're going to sketch this guy out to look like this. So this is our pulse width, lowercase a, and our amplitude, uppercase A here. So capital A is the pulse height, lowercase a is the pulse width. So we want to determine what's the Fourier transform if we take this signal in time and we want to understand what it looks like in the frequency domain. So we're going to use Fourier's hypothesis that we wrote out, the definition of Fourier transform from a couple slides ago. So what are the components in the frequency domain? It's going to be 1 over the square root of 2 pi from the integral -infinity to infinity, our signal in time, ei omega t dt. So we're going to apply this where we're going to plug in for f of t, our top hat function here. So I'm just going to cross this out and I'm just going to write our top hat is what we're going to use here. So if we apply this and looking at the properties here, we can change the limits of our integral. That's the first thing that we can do. So I'm going to have 1 over the square root of 2 pi. That is equal to 0 everywhere except from -a over 2 to positive a over 2. So we can simplify that out. And we know that at all those values that our top hat function here is just a constant. It's capital A. So we can pull that out and put that out front, our constant. So our capital, our amplitude there, negative A over 2, positive A over 2. So we're left with the exponential term here. So we can evaluate this integral where we have 1 over I omega times E I omega t. Evaluate from negative A over 2 to positive A over 2. We can plug in those values and we're going to get e to the I omega A over 2 minus e to the negative I omega A over 2, all divided by I omega. So to simplify this down, we're first going to do a trick of we're going to multiply this by 1, where 1 is equivalent to 2 divided by 2. So that is the first thing we're going to do. And I'm going to bring this up here. So that's going to be 2a over the square root of 2 pi times e I omega A over 2 minus e negative I omega A over 2, all divided by 2 I omega. We did this so we can use the trig relationship where the sine of x is e I x minus e negative I x divided by 2i. So using this trig relationship, we can then write this in a different form. So we have 2 capital A divided by the square root of 2 pi times sine omega A over 2 divided by omega. We're going to simplify this down again and by multiplying by 1, where 1 is going to be A over 2 divided by A over 2. And when we multiply by 1 that way, we get the following expression. We're going to get capital A times lowercase a divided by the square root of 2 pi times sine omega A divided by 2 over omega A divided by 2. And the reason that I want to get this in this expression is it's a very special function called the sine cardinal function. Which is also called Sinc function. And it has the expression, so Sinc of x is equal to 1 if x equals 0, and it's equal to sine of x over x if x does not equal 0. So we can write that the Fourier transform of a top hat function is going to be the amplitude of that top hat function times the width of that top hat function divided by 2 pi, the square root of 2 pi times sinc omega A over 2. So the answer to what is the Fourier transform of a top hat function? It's a sinc function. So giving you a little bit more detail of what this sinc function is, I have a sketch over here. where you can see that for omega a divided by 2 here, or a sinc function, you can see that it crosses at 0 here at multiples of pi, negative 2 pi, at integer multiples of pi here. So it has an oscillating feature just like a sine function, but it decays as you get further out and further out here. So this is because the sine of x equals 0 when x is equal to an integer multiple of pi here. So with this type of pattern, I don't know how much optics you guys have worked with, or if you were able to do any optics experiments before the pandemic at all. Have you seen a type of pattern like this before in any optics-based experiments? So this looks very similar to a diffraction pattern. Where if you ever did like the single slit experiment, that you might see in classical wave theory. And the reason that you see this type of sinc function is your top hat is going to be equivalent to the slit that you're passing your light to. And the diffraction pattern is then the sinc here. So overall, we can say that the top hat function of a width of a for a given value x, its Fourier transform is going to be a sinc function. So I'm using this arrow to represent the Fourier transform, and then I can draw an arrow this way, and that represents the inverse Fourier transform. And I'm using x and p as the conjugate variables. So this is the most generic way to write this instead of using time and frequency. And I'm using this notation because that's what's in the student's guide to Fourier transforms. So with this notation showing Fourier transform, inverse Fourier transform, what we can call this is that a top hat function and a sinc are called a Fourier pair. Just to add another definition that is Fourier something. Fourier pair means that you can go in between those two using a Fourier transform. So we could say if you have a sinc function in the time domain, you'll have a top hat function in the frequency domain, or vice versa there. So a numbered top hat, understanding that's always a sinc as function number 1, sinc is the second function there. So any questions with that derivation at all, or the concept of the Fourier pair? Okay, if not, we'll move on to the next useful function to know, which is the Dirac delta function, which isn't, a delta function isn't in the lab, isn't real, but it's an ideal function. It's an ideal point pretty much. So it's where the function is 0 everywhere. I guess I'll just write 0. Except, we're going to keep it simple, except at a time value of 0, and its amplitude there, or the integral there, is going to be 1. So it's called the Dirac delta function because Paul Dirac conceived of it in 1930 to help him with some work. But there's also, historically, there's many other famous scientists, Cauchy, Poisson, Kirchhoff, Helmholtz, Kelvin, like all the names on the Rockefeller building, where they've come up with similar concepts like the Dirac delta function when they were trying to work with like point sources of like waves or heat, or for Dirac like quantum objects. So it's a concept that was well established before Dirac, but his name's gotten associated with it. So mathematically, with this oral, I guess, definition that I've written out here, what we can say, we're going to call the delta function a lowercase delta. It's going to be 0 everywhere unless t equals 0 here. So delta of 0 is going to be equal to infinity. And if we take the integral of the delta over all time, it's going to be equal to 1. So that's our mathematical definition of the Dirac delta function. So it's also worth noting that the Dirac delta function is equivalent to the top hat function as a approaches 0 here as well. So that's what we're going to use. This relationship between the delta function and the top hat, viewing it as a limit, is what's going to lead us to our answer of what the Fourier transform is of a delta function. So if we want to understand the delta function in frequency space, we can say, okay, we know that the Fourier transform of a top hat function is a sinc. So we can say, we can start with that point and write out the relationship we just derived of the sinc function. So this is when a is going to 0. So if we plug in a is going to 0, if we keep decreasing a so it gets closer and closer to 0, what we would get is, if I poorly draw out the sinc, is that it'll keep broadening and broadening out. If you remember, I said to you guys that as things get narrower and narrower in the time domain, they get wider and wider. There's an inverse relationship between the time and the frequency. So if we keep, as a is getting closer to 0, this will broaden out more and more and more. And at that limit, what you're going to get is a straight line here. So what you'll get is going to be, in the frequency domain, you're just going to get a constant, and that value will be 1 in the simplest way. So for the Fourier transform for a delta function is a constant, is the takeaway from this. And we can write this Fourier pair then like this. And I'm saying generally a constant here. I'm writing it as 1 over here, and that's only if you have proper normalization shown there. So physically, what this means, or I guess maybe not physically, what does this mean conceptually, physically, whatever. So it means the Dirac delta function is a limit of like the sharpest function that you can produce. So an infinitely sharp function in time requires equal contribution from all frequencies. That's what this constant line means here. That if we go back to our definition from last lecture of the Fourier hypothesis, your AN and BN would be equal for every single frequency component that you there. So the sharper your signal is in time, that means the more frequency components it contains. So this is an illustration of that inverse relationship. Of time and frequency here. And in the lab, you guys will, and in the MATLAB simulations in lab 2, you guys will be playing around with as you sharpen, if you expand or shrink in time, guys should be able to visually see this as well. So any questions with the delta function and the constant? Okay, I think we have about 2 more to go, I think. Yeah. Okay. Next one we're moving on to is the Gaussian function, which hopefully you guys have encountered a Gaussian function, or you could say normal distribution, or a bell curve. Maybe in your biology classes in high school, you talked about the bell curve as well. And it's named after Carl Friedrich Gauss. I have here a postage stamp from Germany that was in his honor. There's been Google Doodles, I think, for him as well. But if you look into the history, you can see his birth dates here, 1777 to 1855. But he was a big name in math, just as an aside of a little bit of history, that he didn't believe in like publishing frequently. He liked few but ripe publishing. And after he passed away and they dug into some of his notes and records, they said that he probably slowed math by 50 years by just like not publishing and sharing his results. And the things that he did publish, lots of times he didn't include the proofs. He would just say that he would suppress for sake of brevity, is a quote from one of his writings, that he was like, you guys can figure that out, let's keep it short. And his sons, some of them wanted to go into math, and he said, nope, I don't want you guys to lower the family name and screw up my name because you guys aren't going to be as great as I am and stuff. So that's just some interesting backstory that, yes, he played a huge important role in defining the Gaussian function, but some of his history, maybe not the nicest of guys to even his own children and the like and stuff. So the reason that I mentioned the normal distribution or bell curve, or I'm guessing that you guys have seen this in your other classes, because the Gaussian function is very useful to represent random probabilities. Or another word for random probabilities is a stochastic process. So you can represent a Gaussian function. If we sketch this out, what a beautifully straight x-axis there. Is that we're going to represent this with an amplitude of capital A, and we're going to represent the width. You can represent the width at different points where you commonly see full width, half maximum. So that's the width at A equals to 0.5 A. And we're going to define that as the full width half max FWHM. That's going to be equivalent to 1.665 times this constant, lowercase constant A. So if we write that out mathematically, we're going to use G for our Gaussian function. Here, the T being in the time domain, we're going to say it's going to have an amplitude, capital A here, times the exponent negative T squared over lowercase a squared. And this is for something that's centered at 0. That if you wanted to shift it, you would then have an additional constant up here with the T. So if we wanted to shift that, it would be AE negative T minus T naught, well, that guy squared over A squared there, if you want to shift. So if we applied, if we want to get at what is the Fourier transform, what are the contributions in the frequency domain, applying the equation that we had, we'll plug in the Gaussian function. I'm going to pull out the capital A, our amplitude, since that's a constant. So this is our component of G of T here. We're going to multiply that times E I omega T, integrating over all space dt here. I'm not going to go through the whole derivation here, but know that we're going to apply Fourier's trick to reach the output here. You can read chapter 1 if you want the details of the whole derivation. But what our output looks like, our Fourier transform in the frequency domain looks like the following. We have lowercase a, capital A, those constants divided by the square root of 2 times e to the negative a squared omega squared divided by 4 is what the end result is. So looking at this function on the right-hand side here in the frequency domain, what type of function does this look like that we've talked about in today's lecture? What shape would this have?
Would it also be like a Gaussian?
Yeah, Jack's right that this is also a Gaussian. In frequency. The difference here that you note is that you have, I mean, the amplitude is going to be slightly different. You're also going to have this factor of 4 down here at the bottom. So what this is telling us is that the Fourier transform of a Gaussian is another Gaussian. You can see that the a term, this a squared term here, is now in the numerator instead of the denominator. So that's telling that the full width half maximum of the Fourier transform is going to be inversely proportional now that it's in the numerator. That's the key takeaway here. And this has a role if we're talking about conjugate variables. And I think last lecture we talked about how time and position are conjugate variables. If you think of quantum mechanics, this inverse relationship between a Gaussian and its Fourier transform and the width of that has to then play a role in the uncertainty of signals. So if you're measuring a signal, many times you're representing that uncertainty with the Gaussian, it should be normally distributed. So that's where you might see this come up again. How certain are you in that signal, I guess, relating to the earlier lecture. Okay. Then finally, pretty much finally, we're going to go over the exponential decay as the last signal that's useful to know. It can be an exponential decay. It can also be an inverse exponential growth. Those have very similar, depending which direction it's heading, if it's positive or negative. So we're going to write our signal in time for the decay. It's going to be an amplitude with some decay with some time constant there. So the time, we have an exponential decay. This time constant, lowercase a, is going to be at the value of a, capital A, divided by the value e here. And this is just a good thing to know about exponentials as well. So if we did the Fourier transform, again, I'm not going to go through the derivation of this guy. It results in a complex function. Complex meaning that there's an imaginary term, that if we do the Fourier transform, we get capital F of omega is going to be negative capital A over I omega minus 1 over A. We don't really want to work with a complex function. It's not easy to plot. Let's try to get a better understanding of this by taking this power spectrum, where the power spectrum is, we're going to go over this. This is going to be important in lab 4 quite a bit. We're going to go into more detail of this, but a power spectrum, when we first write it mathematically, is going to be the square of, it's going to be the frequency spectrum times its complex conjugate here. And the reason that it's worded as power spectrum is it's going to be representative of power per unit frequency. And the reason that we're taking this and looking at the power spectrum is because that's actually like a named function that's useful. So if we take the power spectrum here, it'll show up as capital A squared times lowercase a squared over omega squared a squared plus 1. And the form of this power spectrum, we're in the frequency domain here, is this expression here is a Lorentzian function, or a Lorentzian profile. And it's similar in shape to a Gaussian. I do want to note it's different. It's different for important reasons, and we'll go over that in the next slide. But similar to a Gaussian, we can say that the full width half max is a way to characterize a Lorentzian, and it's 1 times pi over A is a property to know. So the Fourier pair of an exponential, or the Fourier pair of an exponent is going to be a Lorentzian here, is what we're going to say. And I want to point out and go in a little more detail, the Gaussian versus Lorentzian. So the Gaussian is shown in red here. We can just say this is arbitrary units time. We can say arbitrary units or the frequency versus Lorentzian shown in blue here. So some things to note is that at the full width half max, maybe this isn't the best plot here, but this isn't very nice plot. If we actually calculated, I think this plot was designed to have the same full width half max and same magnitude to emphasize how it extends out. But the Lorentzian should be narrower at the full width half max. I'll put bad plot here, sad face. I did a bad job picking that. So the full width, Lorentzian is narrower at the full width half max, but this plot does show that it decays to 0 slower than the Gaussian. That's what this plot represents. So there are differences just inspecting it visually here. But the important thing, you guys are physicists, you guys are engineers. So think about when you're using, if you're trying to fit an equation or if you're trying to fit some data to an equation, that the Gaussian and Lorentzians are used physically to describe different things. So I already mentioned Gaussians are about random processes or stochastic processes. So a Brownian random walk that you may derive in StatMech, or flips of a coin, or you'll also hear Markovian processes are what Gaussians are used for. Lorentzians you'll see shown up in physics and applications with resonances or vibrations, where time comes into play as well. So random chances over a given time. So you'll see this show up in spectroscopy. So if you have an atom, if you have an electron in an atom or electron in a molecule that is in an excited state, and then it has a certain probability of going to the ground state and then emitting a photon or light there, that the full width half maps of Lorentzians usually relate to that probability. You'll see spectroscopy this show up. So if you are having some data where you see a curve that has shapes similar to a Gaussian or a Lorentzian, don't just say like, oh, I'm going to try both and see which one fits the best, and that's what I'm going to use. No, you should think about the physics behind what's going on. What's the fundamental process there? Does it have to do with random and stochastic processes? Does it have to do with resonances? Or does it have a time dependence there that will indicate which one of these is more appropriate there? You shouldn't just say like, oh, I'm just going to pick whatever fits best. So I just want to note that as well. So, okay, maybe I lied, that would be the last one. I do just want to note two other functions quickly. We're not going to derive, but a Dirac comb is going to be a series of delta functions over time. So if this is a single delta Dirac delta, this is a Dirac comb where you have a series of equally spaced Dirac pulses that are spaced by a given time. We're going to say tau here. That the Fourier pair of this, like this is why we're not going through the whole derivation here. We're going to represent a Dirac comb with this Cyrillic letter because it looks again like this, the signal itself. That its Fourier pair is going to be another Dirac comb, where the period between those is inversely related. So another case of showing how time and frequency are inversely related. So I'm mentioning the Dirac comb because you can visualize when you're discretely collecting data at certain time points. A Dirac comb is a good way to approximate that it's going to be 0. This is your data collection frequency at each of these arrows here, and it's going to be 0 everywhere else, where you're going to have a convolution. We're going to talk about that later, of a Dirac comb plus your signal as well. So this is important with discrete signals, digital Fourier transforms here. Again, talking about that, we have discrete, real experimental data, as opposed to if you took a Fourier transform class, a Fourier class in the math department, they wouldn't care about that. But in physics and in engineering, you really care about, this is going to be discrete, real data here and not continuous. The other function that I just want to mention is a derivative of the top hat, where we're going to call this a heavy side function, where if this is our time, again, it's going to be 0 everywhere except at a certain time point. It's going to go up to a value of 1. So this is called the heavy side function or step function. In lab, you guys will try to program this where it has the mathematical properties of equaling 0 for times less than 0 and 1 above that if this is centered right at that 0 axis. And if we did a Fourier transform of that, it's Fourier pair where the Heaviside function is with h of t in the frequency domain. That's going to be a delta function at a certain frequency shifted by I over that frequency. So thinking back to when we did the Fourier transform of a delta function, it was a constant. So that's kind of what this Heaviside function is. It's going to be a constant for a whole bunch of values over here. It's going to be 0 somewhere else. So this is kind of like an infinitely sharp step. So the step over here contains all frequencies, but it has a phase shift where it's 0 here. So this is accounting for the 0 components. This is accounting for the areas where it's 1. So that's another one worth noting. But not as much detail. So going over all these functions that are useful to know, let's go over what these functions are with their Fourier pair. So if we have a sine, we didn't derive this today, but we talked about it in the last class. So if you have a sine wave that has just a single frequency component, what would its Fourier pair be? Think back to last lecture where we did that sound wave. What did I sketch out as the frequency representation of that sine wave?
Would it just be like a vertical line, or?
Yeah, so that would be similar to what function did we talk about today that looks like a vertical line?
Delta.
Yeah, delta function. Let me bring up the chat too. Yeah, so Riley also said a delta function. So we can write that as at a certain frequency omega here. So we also talked about if you just had a delta function where we defined it exactly at 0 there, what was its Fourier pair today? If you have a delta function centered at 0. Yep, so Riley says 1, it's going to be a constant. It's 1 if it's normalized. If we have a delta function that's shifted slightly, that's going to be a slight phase shift with that constant. And if you have, I'm just going to write these guys out. If you have multiple delta functions at a given time shifted away from each other, that's kind of like what we're talking about with the sine here. That'll be like a cosine, depending where you're at. We talked about the Dirac combs, and these are, I mean, I know this is a lot of detail for different delta functions that we didn't go over in tons of detail, but I'm going to say again, look at chapter 1 in that student's guide. We talked about the Dirac comb will be another Dirac comb. And we talked about the top hat. What's the Fourier pair of the top hat? Yeah, so Dina says a Sinc function. Then we talked about, so square wave, we didn't talk about this. The square wave is going to be very similar to like the top hat, but you're going to have that be periodic as well. So its Fourier pair is going to be pulses with amplitudes that scale like this Sinc. some of these guys like the square wave, you guys will be going over that in lab. You'll also be doing triangle waves, sawtooth waves and the like. So I'm explaining this right now, but you'll see it in lab as well. And then last two, I want to say Gaussian, what's its Fourier pair?
Also a Gaussian.
Yeah, Jack and Riley, another Gaussian. This is in the most simplified notation. And then we have a Lorentzian. What is its Fourier pair? One of the last ones we did. Fourier pair of a Lorentzian.
Guess, is it another Lorentzian?
No, so the Gaussian and the Gaussian are, I guess, identical pairs. But what's the last one that we've talked about? Okay, Dina's got it, exponential. So yeah, I switched it up and talked about that. So yeah, so that's a quick overview of those signals. So when you guys are in lab and you're going to be sending in pulses of an exponential or a square wave pulse or a sine, look at what the output is, but also don't forget that we did talk about this in lecture when you guys are going over the answers. Think before, when you're sending in that exponential, say, okay, what do I expect to see? And based on what we talked about here, what derivations we went through, and then see what you do see. Is it actually a Lorentzian? Or are you seeing something else? Are you seeing something that looks like a signature of just part of a Lorentzian? Because the derivations we did here are for continuous signals. So if you have discrete signals, how might that change what you're seeing in the lab? So those are some things to think about. And I'm just pointing out, don't forget what we talked about in lecture when you guys are in lab. And you can refer back to these notes as well. But not everything will be perfectly identical and the like, so for what you're expecting. So that's why I wanted to go over today. We do have some time for a little bit of questions, but I do want to point out lab number 2 sign up is available. So please sign up today. I think would be great. Just emphasizing again to work with different lab partners. Unless you're working in a different time zone, then you guys can work with the same lab partners. And I want to point out that parts 1 and 2 are remote. So part 1 is doing the Fourier synthesis just like we did in last lecture, but with a different function. Part 2 is all in MATLAB. So if you guys have MATLAB on your computer and you guys can get that from the software center, you can do that remote as well. And then parts 3 and 4 are in the lab. So part 3 is collecting data with your function generator. So the ARB, the HP function generator, and then feeding that to the computer and doing Fourier transforms in Origin. So having the remote control, having TeamViewer should be helpful for that. And then, so even collecting the signals, you can do all the Origin after if you want. And then part 4 is all with the DSO, so with the oscilloscope. So decide, I think it probably, my advice would be start in lab. And if you guys finish early, then you can work on the remote parts, but realize that also it depends on how bad the snow is tomorrow. Maybe it'll all be cleared out by then, but talk with your lab partner. If you guys have signed up, get in contact before lab tomorrow to decide if you want to start right with the experimental stuff or if you'd rather start with some of the remote things. Also, I'm guessing that my commute tomorrow might be a little bit longer, so I'm not going to have office hours, but if you want to meet with me, just send me an email. So that's just for tomorrow's office hours. So with that, are there any questions at all?
I have one quickie. So are there still 7 people who are doing the in-person lab?
Yeah, so I think I noted, and I think, let me bring this up. Yeah, so I noted that Sophia gets first dibs on in-person since she was remote. So I think there's still an offset in the numbers. So if you end up being the last in-person person to go to the sign-up sheet and there's not a slot, then you'll have to do that lab remote. But I'm gonna try to emphasize whoever is the in-person that ends up being remote, that they get dibs the next lab, and hopefully no one will have to be remote twice if they're available for in-person. Any other questions?